Welcome back students to this lecture of refrigeration and air conditioning. So today let's discuss our case number 4, that is when the vapor compression cycle with superheated vapor before compression means before entering to the compressor, the state of the refrigerant should be in a superheated state. So let's discuss this theory first, then we will solve one problem regarding this. Okay, so here students, look here, this is the corresponding temperature entropy and pressure enthalpy diagram of this case. So here this is the saturation curve and this is the saturation curve. As the case suggests, it is the superheated vapor before entering to the compressor. So point number 1 obviously lie outside the vapor dome towards the right. So as you know, the compression is a isentropic or reversible adiabatic process. So process 1 to 2 is your isentropic compression process. Okay, so first look here, this is the higher pressure line, means this is the pressure of condenser. This is the lower pressure line, this is the pressure of evaporator. Similarly here pH diagram, this is the high condenser pressure, this is the evaporator pressure. Process 1 to 2 is your isentropic compression. So in TS diagram, the line will be a vertical line, simple, a vertical perpendicular line to the entropy axis. But in pH curve, pressure enthalpy curve, the line will look like something inclined manner. So this one is your isentropic compression in pH chart. Now from 2 to 2 dash and 2 dash to 3, there is a constant pressure heat rejection in the condenser, and from condenser there is an expansion device where the refrigerant is expanded, that is isenthalpic expansion process is occurred in the expansion valve, that is process 3 to 4, and here that is a as it is a constant enthalpy process, so process 3 to 4 in the pH chart will look like a simple perpendicular line that is perpendicular to enthalpy axis, and process 4 to 1 is your constant pressure heat absorption in the evaporator. Okay, so simultaneously we can draw the 4 to 1 graph in the pH chart. Okay, so after drawing the temperature, entropy and pressure enthalpy diagram, now we are able to find the coefficient of performance. So what is the formula of coefficient of performance? That is refrigeration effect to the work done by the compressor, that is RE by WC. But what is RE? It is the change in enthalpy. It is the change in enthalpy in the evaporator, means H1 minus H1 minus H3 divided by H2 minus H1. Okay students, so this will be, it will be your H1. Okay, it will be your H1. So this is your refrigeration effect and this is the work done, so it will be H1 minus H4, and you know H4 and H3 are same enthalpies, so H1 minus H4 divided by H2 minus H1, and here is also H1 minus H3 divided by H2 minus H1. Okay, fine, up to this you are clear. So now as the point 2 and point 1 are both in superheated region, so apply the properties of pure substance, that is H2 will be H2 dash plus Cp whole into T2 minus T2 dash, and H2 dash will be this one, H2 dash will be Hg dash at the higher pressure, that is condenser pressure, plus Cp whole into T2 minus T2 dash. Similarly, you can find the entropy at point 2, that is H2 will be H2 dash plus Cp ln T2 by T2 dash, and H2 dash will be written as Sg2 dash at the rate condenser pressure plus Cp ln T2 by T2 dash. And similarly you can find the enthalpy at point 1 and entropy at point 1, that is H1 will be H1 dash plus Cp whole into T1 minus T1 dash, and H1 dash will be Hg1 dash at the rate of evaporator pressure plus Cp whole into T1 minus T1 dash, and S1 dash will be Sg1 dash at the rate of evaporator pressure plus Cp ln T1 by T1 dash. So this is your vapor compression cycle with superheated vapor before compression. So let's solve one numerical. Okay, so here students, there is a question. The question says one second. Okay, the question says a vapor compression refrigeration plant produces 28 tons of ice at 0 degree centigrade. Okay, so means the refrigeration capacity is 28 ton of ice. The pressure limit is 5.2 bar and 5.2 bar and 2.1 bar, not 5.2, it is 5.3. okay, because here the pressure is 5.3, so it is 5.3 bar and 2.1 bar. The vapor is superheated at the end of compression. Its temperature is 37 degree centigrade. The vapor is superheated by 5 degree centigrade before entering the compressor. Okay, the relative efficiency is 62%, and you have to find what is the actual COP and mass flow rate of the refrigerant, and you have to take the latent heat of ice is 336 kilojoule per kg, and the Cp is 0.63 kilojoule per kg Kelvin. It is given, and a table is given where pressure column is there, saturation temperature is there, and liquid heat is also there, and latent heat is also there regarding the two pressure, that is 5.3 bar pressure and 2.1 bar pressure. You have to first notice as the vapor is here this line, the vapor is superheated at the end of compression, and its temperature being 37 degree centigrade means this is the superheated temperature, and this one is your saturation temperature at 5.3 bar. Okay, so obviously you can find the degree of superheat. And second point, you have to notice the vapor is superheated by 5 degree centigrade before entering the compressor, means point number 1 will be in your superheated region. Okay, so let's first draw the TS diagram and then solve. So this is the TS diagram and this is the pH diagram. Just put all the data what are given in the question. At point 1 dash and 4, your temperature is lower temperature minus 14 degree centigrade, and 2 dash and 3, your temperature is 15.5 degree centigrade, and it is superheated to 37 degree centigrade. So point number 2 is your temperature is 37 degree centigrade. Okay, similarly it is the corresponding pressure enthalpy diagram. Okay, so let's move further. Okay, so here it is your 5.3 bar pressure line, this is your 2.1 bar pressure line, this is your enthalpy at point 1, enthalpy at point 2, this is your enthalpy at point 3, and point 4 are equal because it is a isenthalpic process. Okay, so what are the given data? Let's see. The refrigeration capacity, that is 28 tons of refrigeration, that is 28 TR. Students, you know the value of 1 TR is 1 ton of refrigeration is 3.5 kilowatt. So you can find what is 28 ton of refrigeration, that is 28 into 3.5, that is 98 kilowatt. So this is your refrigeration capacity. Okay, so after getting this, next we can find the okay, the CP is given, that is 0.63 kilojoule per kg Kelvin. Okay, okay, 0.63 kilojoule per kg Kelvin, and the evaporator pressure is your 2.1 bar, and condenser pressure, and that is your 5.3 bar. Okay, so you know all the temperature limits, so you can easily find the enthalpy at 0.3, that is HF3 at the pressure of 5.3 bar, and from the table you can check what is the enthalpy. It is 56.15 kilojoule per kg. Similarly, you can find the enthalpy at 2, that is H2 will be H2 dash plus Cp whole into T2 minus T2 dash, and from this you can find the enthalpy at 0.2 will be 214.6 kilojoule per kg. Okay, after getting H2, you can find the value of H1, that is just put the formula. H1 will be H1 dash plus Cp whole into T1 minus T1 dash. But here T1 dash is T1 dash, you know, that is minus 14 degrees centigrade, but T1 is not given. But T1 minus T1 dash means it is the degree of superheat, and it is question says the vapor is superheated by 5 degrees centigrade before entering the compressor, means the difference is given at 5 degrees centigrade. Just put the value in place of T1 minus T1 dash. So you can easily find the value of enthalpy at 0.1, that is your H1, which is 186.97 kilojoule per kg. Okay, so now you can, after getting this, you can find the COP, theoretical COP. Theoretical COP will be what? H1, just put the formula, that is H1 minus H3 divided by H2 minus H1. Just put all the value and you can find the theoretical COP, that is 4.73, and the relative COP is 62% minus 0.62. Okay, 0.62. Just what is the relative COP? It is the actual by theoretical. You know the relative COP. Can you find the actual COP? Yes, actual COP will be 62% of theoretical COP. So theoretical COP will be, sorry, actual COP will be 2.93, and this is the actual COP. And you know what is the actual COP? It is the refrigeration capacity by power required to drive the compressor. Okay, and what is the power required to drive the compressor? It is mass flow rate of change in enthalpy in the compressor part, that is H2 minus H1, and from this you can easily find the mass flow rate. Why? Because you know the actual COP, you know the refrigeration capacity, that is your 98 kilowatt, and just in the denominator part, power input, in this in place of power input, you can just put what? You can just put m dot whole into H2 minus H1. You know H2, you know H1. All the data is given except mass flow rate. So you can easily find the mass flow rate, that is 1.21 kg per second. Thank you.